The last topic we're going to talk about is the direct step method for water surface profiles. So the idea here is that we can calculate the distance between two known depths. We could even guess a second depth. If we have a first known depth, we guess the second depth and we can find out how far apart they are. So that's based on this idea of comparing the amount of energy gained as something's going downhill or the water's trying to accelerate downhill due to the force of gravity, and comparing that with the friction that is going to reduce the energy. So if there's a situation where water is producing more friction energy loss than it is energy gain due to gravity, then water's going to slow down. And so it's pretty straightforward. We just need to figure out the methods that we'll use to calculate that. So the first thing we want to do is take a look at how they've developed this. So it's based on the Manning equation. The Manning equation, what we really have used it so far to describe is this idea of something like terminal velocity, where the energy lost due to friction is equal to the energy gained as the thing's trying to accelerate down the hill. So the velocity remains constant upstream and downstream. And so some of the things that we've talked about is this idea of a bottom slope. And we just want to define that explicitly. That's the slope of the bottom of the channel. And then let's compare that with the slope of friction. So in normal conditions, those two are the same. And when I say normal, that means uniform conditions. Those are sometimes used interchangeably. But that's not the condition that we're interested in today. So what we've done is actually, Manning wrote this equation. It's set up just like this. It turns out in the previous video I showed this as being S naught, and that's because when we're going to use this form of the equation, we are going to say that the friction slope is equal to the bottom slope, and we'll know the bottom slope. That's going to be a geometric property. So if we use the original form of Manning and then we rearrange and solve it for the friction slope, and then we talk about, okay, well, we're going from point 1 to point 2. Let's talk about the average friction between point 1 and point 2. And so to calculate the average friction, we'll need to calculate the average velocity and the average hydraulic radius. And so basically the way that it breaks down is that we need to have two known depths. And so we're going to need to have those two known depths so that we can calculate the velocity and calculate the hydraulic radius. Remember, the whole intent of this is that someone's giving us a flow rate, and maybe we've got an existing channel or we're trying to design a channel and we want to know how far apart two known depths will be, or two depths of interest. And we could even put this in Excel and just guess a bunch of depths and generate a water surface profile. So our calculation is going to be, from 2 points. Basically, we're interested in is how far apart these things are. And it's going to be the change in distance for a change in depth. And so here's the equation that we're going to use. Basically, we're going to compare at our two known points the energies. So how much does the energy change between the two known points? And then we're also going to look at the energy that's gained due to gravity, or as this thing's wanting to accelerate down the hill, and compare that with the friction slope or the energy that's lost as it moves downhill. And so we can so let's take a look at it in Excel. So here's the idea. I've got a first point of interest. Water's going over a dam, and it's going to go through critical right as it goes over the top of the dam. And so that's this first known point. And then after that, I just started guessing a bunch of depths. In fact, I've got this set up so that I can just change how far apart these guesses are. And then I calculated the energy and the area and the velocity so that we could get the hydraulic radius and the average velocity and the average hydraulic radius. And then we can do that delta x calculation. And what it does is it will allow you to generate a curve that looks something like this. So here's the bottom slope, and here's the crest of the dam. Here's normal depth. I calculated that separately. And then here's that curve that we just generated. So you can see that the water is getting shallower and shallower, and eventually it's going to get to this change in slope, and that's going to be a mild curve. And so anyhow, what we can do is we can generate something that looks like this, which is a water surface profile with a lot of different things happening. There's a waterfall at the end of this thing. There's the water's going through critical right over the top. And well, I think the best thing to do now would be to just do an example. So this is a pretty involved example. We're going to go through a step. So this is very similar to the first example. The biggest difference now is that we've got a 1 foot bump. So whereas previously the water sort of slid over this bump, now it's going to cause a hydraulic jump. I'll show you how we know that. But so we want to think about this step up as the channels move, as the water's moving downstream. We want to think of that step up kind of like a dam. So the water's sort of racing into it, and then it piles up, hydraulic jump, and then it sort of skirts out the other side. So let's do this example. So it's got all the same info as last time, but I'm going to go through with the spreadsheet exactly how we get all the information. So step 1 is to get everything set up in the spreadsheet. So because we're going to do this in English units, we're going to use the gravity in feet per second. And there's a unit correction because the Manning's N value that we're using is unitless, but it turns out it does have units, and so this is a correction to fix that. The bottom width is 10 feet. We don't know the depth yet. We're going to figure that out. The side slope is 2 to 1. The bottom slope is 0.01, and the Manning's N value is 0.013. Our flow rate is 200 CFS, and on any of these problems, in this problem that we're getting ready to see, this is a test problem. On any of these, the first step is to find out what normal depth is and write some things down about normal depth. So let's do that. So we want to figure out what normal depth is. So we're going to goal seek. This is the thing, Manning Q is the thing that describes normal depth. So we're going to goal seek Manning by going to data, what if analysis, goal seek, and we're going to set the Manning flow rate to 200, which is the design value, by changing the depth. And it's just going to guess values of depth until we get to the answer. And so we've already seen that. We've got our depth of 1.33, and we've got our energy of 3.52. So I'm going to I've got that written down. We'll write it down on the slide. Let's do that again. But now what we're going to do is we're going to find out what critical depth is. So those are two important values that will help us understand how to work all these problems. So what's normal depth and what's critical depth? So critical depth, critical depth is where the Froude number is equal to 1. So the speed of a wave is the same as the speed of the water in a channel. It's kind of a special thing. So what if analysis, goal seek, we're going to set the Froude number, so right here, to 1 by changing the depth. So we get 2.01, and we see the minimum energy here is 2.79. All right, so let's put that into our spreadsheet. So oops. So I wrote in, but this is actually YC. Okay, so normal depth is upstream controls. So I didn't point that out, but if we look at normal depth here, it's less than critical depth. So that's one way to notice that. But also we can look at the spreadsheet and see that the through number is greater than 1. So that means if we go far enough upstream, we'll be at uniform depth. And if we go far enough downstream, we'll be at uniform depth also. But between those two places, we don't know what happens. And I already know that there's a hydraulic jump. I've already worked the problem. So the first thing is to figure out if there is a jump or not. So the easiest way is just to assume that there's no jump. So let's figure that out. To help us, we want to draw out the specific energy diagram. And we're going to draw this a lot. It's not so much helpful to work the problem, but it's very helpful to understand the problem. So if you've got a really good understanding of this stuff, maybe you don't need to draw this thing. But since we're all just getting used to it, we're going to draw it out. So we've got some data points that we can start to fill this thing in. So there's YC. There's YN, there's EC, and EN. Oops. I wrote the wrong value down for the normal energy. Okay, so first thing we're going to do is we're going to assume no jump. And so we've already worked this problem once, this exact same layout, but just with a different step height. And so we know that using the Bernoulli concept that energy 2 is equal to energy 1. Those energies are the depths plus the velocity heads minus the step height. So this step height is 1 foot. And so that is 2.52 feet, and that energy is actually less than the critical energy. And so the critical energy is the minimum energy that's needed to work this problem. It's not possible to flow 200 CFS with an energy that's less than 2.79. So this is not possible. And so what that means is that as the water's coming down this thing, it's going to have to pile up. And so basically the water's going to get deeper before it goes over the edge. And so what that means is that, well, first of all, that there is going to be a hydraulic jump. And also, it's going to go through critical right over this location. So let's call that point 2. We'll call this point 1. So that means Y2 is critical. This idea of the water going through critical as it goes over this bump is one of the trickiest things to figure out. And so one of the ways that I want to try and tie that in is this idea of, well, what if we have a dam? right? So there's water here, and maybe it's a detention basin or something like that. And so as the water accelerates, it's going to break over, and it's going to go through critical right as it goes over that bump, right? It's the same thing here. There's another case where that happens, and that's where we go from a mild slope to a steep slope. So if we had a normal depth subcritical, let's just sketch this out real quick. So here's critical depth, and here's normal depth. So there's a mild section and then a steep section. This is another case where we know that the water will go through critical right as it breaks over. So downstream of that is an S2 curve, and upstream of that is an M2 curve. And so that's why it's really important to practice these, or to at least start to familiarize ourselves with water surface profiles and where things like critical happen. There's one more place that critical might happen that we can be sure of. If we had a mild channel and then a waterfall, right? So Niagara Falls. So it's going to look like this. It's going to go through critical basically right just a little bit before the falls. And so again, that's an M2 curve. So now on our problem, it's going through critical right here, and we're going to go downstream like that. So that's an S2 curve. And then there's sort of a local change, and it goes up to here. So it does actually get deeper as it goes upstream. Then there's this S1 curve, hydraulic jump to uniform depth. So the other thing to keep in mind is that it's sometimes, especially for people that are new to this, is like, why does there have to be a hydraulic jump right here? All right, so the idea is basically that from this point upstream, everything is upstream controls. And so what that means is that the water sort of coming downhill. If you imagine being a piece of water, you're racing downhill, and it's almost like you just can't see what's going on in front of you until you smack into this hydraulic jump, and that's because a wave cannot propagate upstream. Okay, so that's true. Here, let's take a look at this point. So from this point, we have, as we go downstream, upstream controls. And as we go upstream, downstream controls. And the reason is that right here at this point, it's critical depth. If we go just a little bit upstream, because the channel is getting deeper, the water's slowing down. And so that makes it subcritical. And so it's subcritical all the way to this point, and it maintains that subcritical downstream controls all the way until we get to the hydraulic jump. And so a hydraulic jump is actually a location where there's a conflict of controls. Upstream, we've got supercritical water racing down. It's upstream controls. And then downstream, we've got subcritical water that's downstream controls. And so those two directions control the water surface depth until you have the hydraulic jump. So that's one of the tricks that it takes a while to get used to, and really that's the reason that we're going to do just a ton of examples. And so we can actually put that point in, and if we wanted to, we can go ahead and sketch out what the downstream part of this is going to look like, because so we actually know this point now. This is a known point, and we know that normal depth is supercritical. So that means that after it goes to critical, it's going to accelerate. It's going to go supercritical, and this is, another way to think about this is that this is a steep slope, and we know that because normal depth is supercritical. And so what that makes this is, that's an S2 curve. So we're going to need to start thinking about labeling these. And so then we've got this local energy change, and so the water level is actually going to go up, it turns out. And so to get to point 2, we're going to use the same energy balance concepts, but we're going to work in the opposite direction. And so what we've got is the energy at 1 is equal to the energy at critical. And then now it's plus 1 foot because we're actually adding as we move from location 2 to location 1. We're actually going to transfer the Bernoulli sum elevation head into specific energy. So we're trading off specific energy and elevation. So the energy at section 2 then is 3.79. Sorry, that's section 1. And then we're going to use that to get Y1 in the spreadsheet. Let's check that out. Oops, here's where we're going. So we need to get this energy to be equal to 3.79, and so the trick is that there's two specific energies. There's two depths with that same specific energy, and so we want to make sure, because what Excel is going to do is it's going to minutely change the depth and see if we're getting closer or farther away from the thing that we're looking for. And so we want to make sure that it's on the correct part of the curve to guess and converge on our specific answer that we're looking for. And so if we look at our drawing here, we're looking at this point. So that's the energy at section 1. It's 3.79. And we're looking for this depth. And so, if I had guessed a point here, it would actually converge on this answer, and that's not what we're looking for. We're looking for this answer. So let's put in a first guess. We're going to put in a first guess that's up here somewhere, and then it will guess the right answer. I'm going to just put in a really deep depth, and that makes sure our Froude number is less than 1. As long as the Froude number is less than 1, we're going to come up with the right answer. So we're going to goal seek our energy. So our answer is 3.63. And in your notes, maybe you want to write goal seek. So we know this depth now. And so then we can actually sketch this thing out. It's going to look something like this until we get a hydraulic jump, and it will jump straight to normal or uniform depth. And so so we've got a hydraulic jump that we need to analyze. We're going to use our specific force concepts for that. So we're going to go from this side of the jump to this side of the jump. And we went through that example previously. This is the idea that if we look at impulse momentum, this idea of a jet striking a plate, what's the force on the plate? That the forces of the water on the inside, on the inflow and the outflow are going to balance out. Otherwise, this hydraulic jump would be moving. So, so what we need to do is we don't know this depth yet. Let's call that section J. But we do know this section right here because that's going to be normal depth right there. It's going to be normal depth or uniform depth all the way along because the water is going supercritical. That means upstream controls in it, so it doesn't see what's happening. It's not affected by what's going on downstream. So the water is racing along, and then bam, it hits the hydraulic jump. And from that point, it's going to jump from this specific force that corresponds with normal depth. It's going to jump to the specific force, which is the same, which is called the conjugate depth. And so if we wanted to look at a plot of specific force, it has the same kind of shape. It's not exactly the same, but it turns out that this point is the critical depth. And then here's our normal depth. Specific force for normal depth. And then there's a conjugate specific force. So these are called conjugate depths. So what we're looking for is, what is that depth? Y, and we're going to call that yj for now. So what we're trying to find out is, what's this thing? We need to know that depth. So to do that, we need to know the specific force associated with our normal depth. So I didn't write that down earlier, but we need to get it now. So let's do that. So again, we're going to goal seek to get to the normal depth. All right, so here's our specific force, 84.21. And then what we want to do is we want to find the depth that corresponds with that same specific force. So so this is the supercritical specific force. We want to find the subcritical conjugate depth of that specific force. So I've got to guess a first value that is subcritical. So I'm going to just guess a large value for depth, and then we're going to goal seek specific force. We're going to set it to 84.21. So it's just going to guess depths until we get 2.86. The units on specific force are something like feet cubed. It's strange units, but that's the answer. So now we know the depth at J. So what we need to do now is figure out what's the distance between these 2 points. And that's going to be the direct step method that we're going to use. So you can see we have 2 different depths that are known. We've got this thing for y1. We know y1, and then we also know y sub j. And so those are these 2 points right here, and we're going to figure out how far they are apart. So to do that, we need to know the energy at both of those points, we need to know the velocity at both of those points, and then we need to average those. So let's do that. So starting at this point, we're going to do our delta x calculation. So if we go to our spreadsheet, we're going to be interested in the upstream part is going to be section J, and the downstream part is going to be section 1. and we need to know the energies, and we need to know the velocities, and we need to know the hydraulic radiuses, and I looked at those in the spreadsheet. We also need that same information for section 1. I wrote that down wrong. And then we need to get the average of the velocity and the hydraulic radius. So that is we're going to use these values for our delta x calculation. So what we need to do now is we need to get that average slope of friction between those two sections. So SF bar is so we're going to use that in our delta x calculation, and it had better be less than the bottom slope of the channel because we know that it's subcritical. It should have less friction loss. So let's do the delta x calculation. And so the answer is 65 feet. So what we're saying is that there's 65 feet between the location of the jump and the inflection point of the bottom of the channel. So like I said, this is a test question. This is a question I could give you on a test. And we're going to do a bunch more examples. So if you feel like this is overwhelming, I'm very comfortable with that because there's just a lot of little nuances. So for example, like we needed to know that what was going on at section 2. So we needed to be able to say like, hey, right here, it's going through critical. And if you couldn't make that, then you couldn't finish the rest of the problem. So what we want to do is we want to try and simplify some of the calculations. And what that means is automating them. So I want to show you that, how I did that in the spreadsheet. So the first thing I did was set up a location that I could copy and paste numbers from so that I didn't have to hand code the numbers in for that for the calculation. So let me show you how it works. First thing we want to do is go to section 1, or sorry, the jump. That's the upstream part of the delta x calculation. And so for the jump, we got our depth was 2.86. So we've got that in there. And all the information that we need to do the calculation is right here. So I'm going to just copy that. And then down here, this is the upstream portion. This is the downstream portion. So I'm going to paste right here. And I got to paste the numbers. And the reason that I'm pasting the numbers is because these cells, if I paste the cells or the equations, it's going to reference what's going on up here. And if I change those numbers, it'll change them down here too. And we don't want them to change. We want them to stay fixed, because now what I'm going to do is I'm going to go put in the data for the section 1, the downstream part of our delta x calculation. So we need to find that again. The depth was 3.63 feet. So I'm going to copy that and paste it here. And so we got 64 feet this time. That's because I didn't goal seek to find this value. But so it does the SF bar calculation for us automatically. You can see how it's set up. So we've got our velocities here, and then we're going to average that out. So you can see that we're averaging these two numbers. And then same thing for hydraulic radius. We're averaging the hydraulic radius. So then we do our SF bar calculation. So I've coded in the value for N and the unit correction. And it spits out SF bar. And then for the delta X calculation, it's referencing these two energies, and it's referencing the bottom slope and then the friction slope. So in terms of calculations on a test, this is the test. This is a test problem. I probably started to run out of some space here, but there's a couple more data points that we should put in. So that's an S1 curve. This is uniform. And if we go far enough downstream, this will be uniform. So that's our first example. It seems pretty scary a lot of times. Maybe you're right on track, and that's great. But I'm going to just do a ton more of these examples. So expect that to happen.